Okay, we left off here on our chapter on thermodynamics where we were going to start treating reactions by the heats that we found previously using that MCAT, right? And so this example basically we walked through, and this one got you to finding the amount of heat for a reaction. Let me go full screen here. Okay, so why is this important? How is this useful? Chemists, this is the combination of the scientific world, is chemists are the ones that go into a lab and use the bomb calorimeter and discovered and come up with the heats for all of these. And then they're tabulated and whatnot, and anyone can use them. And you could extrapolate these things out, budget things, and then engineers use them in chemical plants, et cetera, to make products. And in coming chapters, we'll talk about the products and how chemical reactions have changed the course of human history and whatnot. Okay, so how does a chemical engineer, chemical plant use these values? Is this tells them how much heat they have to remove or how much heat will be required to do something. Right, and we already covered this slide, so I'll just go through this one kind of quick. But really what why this one's important is what we're going to do is at times you'll need to flip or multiply these different heats to get them to add up to a full equation or combinations of equations that you're doing. So this is useful for engineers because they don't need to go and do the chemistry. They can just flip flop and play with the equations and know whether something will work or not. All right, so critical on this slide is, right, this is what you're used to. You know, if you've ever had a barbecue, campfire, etc., charcoal coals are basically solid carbon. They combine with oxygen, they give off CO2, and this is the heat that comes off that you use to cook your food. All right, this also goes into global warming and everything. We'll see at the end of this, but you see it on the news and hear all about it. This is one of the problems, highlights one of the problems, is that the heat, right? It takes a lot of energy to force CO2 gas back into these separate elements of carbon and oxygen. And then the part that's missing from this that you'll cover in Chem 162 is what's called entropy. And the difficulty with this is that CO2 is a gas dispersed in the air, right? Whereas the reverse reaction, they just mine coal out of the ground and it comes in a chunk, and you basically just like we do on a barbecue, you just throw the charcoal on the barbecue. All right, and then this one here below is when you multiply your reaction by some integer, you multiply the heat by that same integer, right? So here they doubled it. So if you have twice as much charcoal, you get twice as much heat. Okay, so let's use that. And this comes to Hess's law. So again, it's not a history class. If you're going to take Chem 162, you will see Hess's law again on the cover, on the chapter of thermodynamics, when we cover this in greater depth. And what Hess's law is it's just saying that these changes are stepwise processes. And what you experience overall is just the sum of these. And if you have gone hiking, then you've experienced this, right? Wherever, all that matters is where you initially start to where you finally end, not your stops in between, right? And so that's what this picture here is trying to show you, is you have two reactions. One is endothermic, you have to put heat in to get there. So A plus 2B gets you to C. And then your next reaction, C turns into 2D, you get this heat back out, right? And so the overall is the purple. You just add the two together. Okay, So let's do an example. And this is a rather challenging example first to start on. So here we've got, let's call the top one reaction 1, the next one reaction 2, and the last one reaction 3. The way I tackle these is, and these are easier for people that like puzzles. It's basically a logic problem. Is you want to look for things in the sum, the overall reaction. So we need to manipulate these reaction 1, 2, 3, so that when we add them all up, it looks like this overall reaction we see at the bottom. All right, the thing that jumps out to me is this HNO3. It's on the product side, so we don't need to flip reaction 2. But it's got a 4 in front of it instead of a 2. So the first thing I notice is that reaction 2 needs to stay as it is, not flipped, but divided by 2, which means we're going to divide the minus 255 in half. Okay, everything else kind of is complicated with NOs and O2s and everything. So as I kind of scan through it, the other thing that catches my eye is the NO2, right? Here's NO2. It's not in equation 3. And equation 2, we already decided what we have to do with that one. And so the only place that it's at left is equation 1. NO2 is here on the product side. And that's not where we want it. So I know now that I need to flip reaction 1, which means it'll go from 173 to plus 173, right? Negative to positive. And then it's got a 2 in front as it's written, but a 3 in front in the summary. So I know I need to flip reaction 1 and multiply it by 1.5, right? 2 times 1.5 equals 3. So once you know what you have to do to 2 things, all that's really left to do is manipulate the third one into having things cancel. Right, so the first one, we flip it, we multiply it by half. Second one, multiply by 1/2 or divide by 2, right? Same mathematics, right? And then either if you could see it, then you can manipulate reaction 3, or if you wanted to, you apply multiplication and then start crossing things out and find what's there. What I noticed is that once we multiplied reaction 1 by 1.5, there was then 3 of these NO molecules. And here we have 2, which means that we flipped reaction 1, right? So we needed to flip reaction 2 as well, so that these two, but not multiplied by anything, these 2 NOs would cancel the 3 that would have happened up here, right? These right there, 1.5 times 2 NO will cancel this 2 NO, and we'll be left with this 1 NO left over. So if you apply those different flippings and multiplications to each, and then you add them all up, they'll cross out. So 3 NOs versus 2 leaves us this 1. Right, there's the nitrogens and 2 cancel each other. 1.5 and 1 is 2.5, and 2.5, so that cancels. And we're left with what the summary was. So this is a good example of what a chemical plant, an engineer at a chemical plant does. Even if it's a new reaction, so say some giant pharmaceutical company like Merck or something is building, making a new medicine, a new drug. They run the reactions on these small scales and they figure out the heat that's involved with them. Then you can manipulate them and use them and multiply them, etc. And then you'll know how much energy and how much it's going to take to make that drug, and how much, if it's minus, that means the heat's coming off. So you'll need to get rid of it, much like a car does with a radiator. All right, so you can clearly see, right, this one is much more challenging if we just go back, right, than this example, right? This was just 1 plus 2, basically, right? This one didn't go through all the manipulations. So this example is pretty challenging. The one on the test isn't going to be this hard. Probably just 2 equations, not 3 like this, but it's the same principle. So if you can, there's some of these on the worksheet and the study guides, but this is these PowerPoints are good to come back and look at, not the videos, but the PowerPoints alone. You can come back and here you can see where, right, if you try to tackle this with, with a scratch piece of paper by yourself, and if you get stuck, then you can just click in the animation and have it help you one step at a time. Okay, standard conditions. So what we're getting to here is the same thing with these heats and chemical reactions, but now we're getting to individual chemicals instead of a complete reaction. So what is the standard state? What this is just defined set of conditions. And it's basically sea level and in a lab at room temp. So 1 atmosphere is where the majority of everyone who does science on Earth lives and the pressure that we all live at. So once you have tabulated, or scientists tabulated these, then much like before, except like the last slides were for a particular chemical reaction, this is for individual molecules. All right, and if it's in solution, which is a little bit rare for these, but it would be 1 molar. We'll see that's important in Chem 162, but not as much here. So that's the standard state. Everything we're talking about this chapter is heat or enthalpy. And what makes a standard state is this little symbol. So when you see this little knot degree symbol, it means that you're at 1 atmosphere, 25 degrees, 1 molar, and that's how much heat it takes to do whatever it is that you've got going on. All right, so last slides, this would be that standard heat of that reaction on the per mole basis of whatever the molar amounts in those reactions were. Now, for an individual chemical, it's called the standard enthalpy of formation. So this little F tells you it's the formation. The little knot tells you it's our standard conditions, and it's the enthalpy change for making that reaction. 1 mole of it from pure elemental forms. The elements are likewise in their standard state. And in general, the delta H, the heat formation, enthalpy of formation for some pure element is 0. And these sometimes make sense when you parlay it or think about it like oxygen in combustion reactions, right? Oxygen is here on Earth, and we need it for combustion reactions, right? To drive your car, you need oxygen. But you don't go to an oxygen store, right? You go to a gas station, right? The oxygen's free. It's free monetarily. It's also free in the heat for the enthalpy of formation sense. All right, so what is a formation reaction? It's the reaction of elements in their standard states to some pure compound, which for us is we're just doing the basics. And this is really what we saw a few slides back, where we had coal and oxygen going to CO2. And there's, in the book, there's an appendix, but these things, that's also on Wikipedia. You just look up some, standard chemical. The value is there with all its constants and standards, etc. All right, so we did CO, and we did CO2 before. There's different forms of carbon, so they have different values. Hold on a second, I'm having thought issues. I assume that's not breaking into my house, but I'll be right back. Okay, I don't know, neighbor's garden or something. I have two Labradors that think they're real guard dogs, but they just sound like it. They're not real. Okay, so heat of formation, right? So here's our elemental forms, carbon and oxygen. This is, as simple as it comes, two elements combining together to form a new molecule. So there's a couple different forms of carbon. So when you go look these up, and I think in a slide or two, it'll show the table. There's different forms of carbon, just like there's different forms of ice, right? At standard conditions, carbon is always a solid, but it does have different forms. There's diamonds, there's graphite, there's charcoal, etc. All right, so we're combining carbon and oxygen, but oxygen comes as O2, right? So it needs to be written like this. And then this isn't balanced. So we've got to do something. You either have to divide the oxygen in half or multiply the graphite by 2. But here's the thing, and you could do this either way. The thing is, it depends on what you're interested in. So usually you're interested in the product or the unique reactant. And since inherently here on Earth, oxygen gas is just in the air, it's usually not the thing you're interested in, right? Since it's free. Okay, so what is a chemical reaction? It's the reactants to the products. So if you knew the heat that it costs to form your products and your reactants, then you could just add up all the values in a balanced equation and take the difference between them. Because again, these heats of formation is your starting point to your ending point. Doesn't matter where you go in between, right? So just like the Hess's law, or if you're hiking, right, the trail goes up and down. The mountain, just like altitude, and all the altitude that you climb is like the enthalpy in a reaction. It only matters the very beginning and the very end points. Okay, if you haven't seen this symbol before, it's a summation symbol. So what this means is that you're going to add up all of whatever is indicated behind. So here it's the heat of formation of our products and the heat of formation of our reactants. And you'll see this common in chemistry. This is a good time to just memorize this. It's products minus reactants for a lot of things we do. It's never the opposite. It's never reactants minus products, right? So then the last thing is the lowercase n. It's the same n that was in the ideal gas law. It's the number of moles. And in a balanced chemical reaction, the n then is that coefficient in front of your reactants and your products. So let's do one here, for example, right? And you can see this is, the Hess's law in action. So if you're interested in methane, natural gas is CH4, combining with oxygen, 2 moles, right? So we're balanced. That gives off 1 mole of CO2 and 2 moles of water. Well, oxygen's free. It's 0, so we don't need to account for it. So really what we're doing is breaking apart methane into its free parts, and that would be carbon, and then 2 moles of hydrogen gas, right? That's 1 carbon and 4 hydrogens. And that cost energy because we haven't gotten to the bonds yet. We need to do a couple more chapters, but we've got 4 carbon hydrogen bonds and we break those apart into its elements. Now we've got all 3 in their elements and we're going to reform them into different compounds, right? We don't have CH4, we don't have methane or oxygen anymore. Now we have carbon dioxide and water. And so this is the most common and classic ones of these heat formation because the human society has been burning fossil fuels and carbon and hydrogen based things now for hundreds of years. And so these 2 are the 2 products that come out, obviously the tailpipe of the car, but anything, planes, trains, and automobiles that has moved things on the earth the last several hundred years. There. All right, it was stuck for a second. Okay, so let's do one where it isn't all plotted out. So this one is C2H2 is acetylene, which is a welding gas, a torch that they use to, melt and combine metals or cut metals. And we're basically going to do the same process here. Oxygen's free. We need to split apart the C2H2. We're going to have 2 of them, and then we're going to get that same CO2 and water values back, but times a 4 and a 2 now. All right, so first, split apart the carbon into 2 moles of graphite, and now 1 mole of hydrogen gas, right? And add those 2 together. Then we've got the graphite going to CO2, right? There's a 4 in front that we're going to need there. And then the water is hydrogen and half a mole of oxygen. And that will need a 2 in front. Right, so to split apart the acetylene, 4 carbons and 2 hydrogen, right? Now 4 CO2 is what comes off. 2 waters. We can add these up and have things start canceling. And like before, the middle part of 2 reactions, so A goes to B, B goes to C. The B is called an intermediate, and it's no longer seen. So when you add these equations up, you get the overall. We were expecting a large negative number. All combustion reactions give off a negative number. The reaction also has 2 moles of the acetylene. And so this number seems reasonable. Right, the carbon and the hydrogen were our intermediates, and thus they cancel out. Right? We go back to the last example. Right, this is the intermediates here. Right, decompose your carbon hydrogen fragment, and then you get back that energy. And so these you never see, right? So if you've ever cooked on a stove with natural gas, methane, you don't see any intermediates. It combines with oxygen, you see a flame, heat comes off. It happens instantaneously. You don't see these intermediates. Okay, so what really happened then? The other way to look at it now with these summations is we just take 4 times the value for CO2, 2 times the water, and then subtract 2 of the acetylene and 5 of the oxygen. Now the oxygen is 0, so you can essentially leave it out. We found we got this 227 from the last 0.4 from the last one, and there's 2 moles of it. And then for every combustion reaction, it goes to CO2 and water. These values are well known. and then sum the two of them and we get the same value, right? And again, we were expecting a pretty large negative number because this is a welding torch that's meant to melt metal. So you're going to need a lot of heat. Okay, so we saw a pretty similar problem way earlier in the chapter. And this is sort of where these things come from, is that all octane is 8 carbons, right? Octopus, and octane ratings, which you've seen at the gas station, right? This is the rating. Combustion means we're combining it with oxygen. Oxygen's free, so we don't care about the value. The products of all combustion are always CO2 and water. So these values are standard and well known. So really, every time a petroleum company makes a new formulation of gasoline, all they have to do to figure out the energy involved with it is just get this value, right? The value for that octane, that C8H18 in this instance, right? And it's a liquid. This is basically gasoline. A gasoline is usually a mixture of things, not just purely one compound. But okay, so we're combining lots of things we've done all semester long here, right? We take our heats of formation and do the summation to get us to the heat of reaction. We have to balance the equation, otherwise we'll never get to know how much heat for just 1 mole of octane. Then in this instance, we're going from the total amount of energy to how much gasoline. So this would be an engineer where you know how much heat you need to do some process, and then they're figuring out how much coal, gasoline, etc. they're going to need. And then when you hand it off to someone who does the business side of it, they're going to factor in the price per some unit of the gasoline and how much it's going to cost, you know, the company to do this type of thing. Okay, so take the reaction and balance it. Notice here this one's got the half mole of O2, but it's fine because the heat of formation of the O2 is 0. So anything times 0 is 0. It's not going to go into the equation, right? And the critical part is we wanted per mole of the gasoline anyway, because that's what we care about. We're figuring out how much gasoline you're going to need to do whatever it is that they're up to. All right, so CO2 and water, right? Oxygen 0, it's left out. This was the critical new one, and not too surprising. You get a lot of heat, a large value. It's got 8 carbons in it, right? The numbers have been getting bigger as our carbon species get bigger, right? The first one we did was just 1 carbon and 4 hydrogens. The next one was 2 carbons and 2 hydrogens. Now it's 8 carbons and 18 hydrogens. So the more carbons and hydrogens, the more heat you would expect to come off, because the molecule's getting bigger, you're breaking more bonds. All right, that's our heat per mole. Now they told us how much energy, and we know how much energy in 1 mole. So then how many grams in a mole? Now we're out of moles. And then they want a bigger unit, not just grams, even though it's a large number anyway. When you buy things in bulk, they do it by kilograms, and then eventually they do it by tons. So our units cancel between our conversion factor we found and then one off the periodic table, then just moving the units, and we get to the amount of gasoline it's going to take to do whatever this is that they're up to. Okay, next here is just going to relate this and talk a little bit about it, and take it for what it's worth. It's a little, I don't know when this book was, the first edition anyway, was probably 10 or 15 years ago, and some of this is opinions and whatnot, but basically what we have here is the shifting of things and combustible fossil fuels that have been used. And this is kind of a strange unit, kilowatt hour. That's a very engineering physics unit. But most of the energy that we use comes from a power plant, or your car, obviously, unless you have an electric one. And then on the eastern part of the United States, they have a lot more coal power plants. But I assume everybody's, cooked at a barbecue with some charcoal, right? Then we don't have methane here in Hawaii, really, to my knowledge, because it's a gas, and so it's usually where oil gets refined and piping is better, so it doesn't find as much use. I don't know anybody with a gas stove in Hawaii, but I've seen them off and on over the years, different places on the mainland. And then this isn't exactly what's in gasoline, but it's pretty close. Right? So here we see our different heat values. You can see they're increasing, right? So the first one, the number is much smaller than methane, but there's only one atom there, right? And then now CH4, methane, or natural gas, there's 5 atoms there. So you're breaking again more bonds. You need, but if you look at it on a per oxygen basis, it's only 1 versus 2 moles of O2, and it doubled, right? So maybe oxygen's kind of a better indicator, right? But anyway, and then here's basically what your car does, right? The number jumped quite a bit up to 5,000, but we've got 8 carbons and 18 hydrogens. Here's fossil fuels cannot be replenished. And this is true, again, that entropy that we'll get into is because the CO2 is a gas and escapes, right? It's hard. It takes a lot of energy to compress gases, and they mix with other gases. So then you've got to separate them out. And if you're a scuba diver, this is one of the reasons the gases can be rather expensive. All right, then this is the debatable part. And I like to think of myself as a much more positive person than some of the people that produce these numbers. So current rates of consumption, oil, natural gas supplies will be depleted in 50 to 100 years. That makes Armageddon, death, and doomsday predictions. I think that engineers come up with green solutions and windmills and solar power and geothermal, and they find new ways to improve gasolines and dig deeper to reach oil fields that we weren't able to reach. And life has continued to progress and get better on the back of science and engineering, I think. So whenever I read these, and if you read really old books, they say we were going to run out already. So it just depends on who you want to listen to. And also, they say common thing you hear with general media is that sex sells. Well, doomsday stuff, negative things sell, and that causes drama and excitement. And so someone who predicts this is going to sell more copies of their book and get more more views of their article than someone who predicts super happy times and parades every day and free energy, etc. Okay, but it's not really a philosophy class. So again, the first copy of this book came out in 2008. So these numbers are a little bit debatable and probably change a little bit. And also these are meant for the mainland. They're not meant for Hawaii. So, but anyway, you can see residential, commercial, industrial, and transportation. And then I like this graph here because it's a little bit historical, and so a lot of this depends on where you're at, right? Hydroelectric, right, is not going to be a big thing in Hawaii. We don't have a lot of lakes and rivers and dams, even though we do have mountains. But it's been fairly steady here, right? It took, this is when computers and concrete and production and drilling and that all it reached its max kind of around the 70s or 80s in the US. And this is because we've kind of moved across the entire country, right? There really aren't any more rivers and lakes, et cetera, to create and dam up and generate much more energy. Right, then there was no nuclear energy before World War II. And then this kind of tapered off a little bit is because these are so expensive to build, and ones that were built in the 70s aren't as efficient as new ones, but it's really expensive to decommission nuclear power plants. And in fact, uh, power plants are extremely expensive to build. Even power companies have difficulties building them and need federal funding and help to do it. Coal, this kind of surprises me that it's still going up because it's sort of a dirty substance, and it also is hard to move, right? You have to put it on a train. So gases are much easier to move, and I think this correlates with the Alaskan pipeline, these two. And natural gas, you get used where you can build a pipe close to either where it comes out of the ground or where it's refined. Okay, so again, it's not, an environmental class, or you've heard me say this, a history class, but we are going to cover some of these things. This is where it overlaps. Our next chapters don't have as much overlap with real world stuff. It's probing into chemical bonds and the atom. So it's good to cover these. This is the time to cover these kind of things. Additives and impurities, we'll talk about a few. Incomplete combustion, and this is why you have a catalytic converter on your car. And these make it into the air when fossil fuels are burned. We'll talk about a few of them. So the emissions of these have several contributions that happen. General pollution, we'll see a few, acid rain, and global warming. And this one, is a little bit hot topic, debatable, depending on your point of view. So this isn't meant to convince you of it. This is just to cover the concept. So CO2, if you've ever been, greenhouses tend to be where the weather is much colder, but the concept of a greenhouse is basically the concept of your car. When you come back from the beach or from school, where your car has been sitting in the sun, and you see commercials reminding people don't leave your pets in the car, is the heat can make it, the light, the energy from the sun goes through the clear windows of your car, and then the window being up traps the heat inside your car. And that's basically what a greenhouse is. A greenhouse is a way to keep plants at reasonable temperatures in places where it's too cold outside, where especially drops below freezing, where the water inside the plants are going to freeze, and that's no good for a tomato. Doesn't do too well when you freeze it. All right, so the way this works is infrared light, which we haven't talked about light just yet, but basically what happens is the CO2 can vibrate and absorb some of that light. And so what happens is it's like a blanket, or it's like the glass in your car that allows the heat to come through and then increases it by interacting with it. All right, and CO2 levels have clearly been steadily increasing because since humans discovered coal and petroleum and started burning them all, the CO2 is the product of that. Okay, so then this button, right, this book's a little old, depending on what you believe in, but it appears as though the temperature is going up. So these models suggest that it's going to continue to go up if it's not curbed, right? This is what the model suggests. So this is sort of politics here and what side you're on. That's not exactly the point of our class. What I would say is that the CO2 going up puts has a greenhouse effect and raises the temperature, then that would cause more severe weather. I like this better. And the problem is these things sometimes take uh, geologic timescales to happen, which is hundreds to thousands of years, not a normal life expectancy of 80 years or something. All right, and the way they study these things, um, before 1960, where we had instruments that could do it, is they look at things in the polar caps. You can drill down, and it's basically, like something you put in your freezer. It's sort of like a time capsule, and the layers of snow tell you these things. Anyway, this is in parts per million. Parts per million is just like a percent, right? A percent is 1 out of 100. And so a ppm is the number of things of interest out of a million. And we can see it's steadily climbing, right? It is going to continue. So renewable energies, this is just going to cover a few of these. The sun is this giant nuclear reaction in the sky, so it would be good to capture more of its energy. And so just the way some of these works, parabolic trough. So if you've ever been on a farm, but even if you've just seen, some cartoons, a trough is what like pigs eat out of, right? They just throw food in a trough, and then the pigs come up and line up and eat it. And so parabolic is a curved shape, and basically what you have is the light shines in the parabola of the trough, and then all the light, and it's made of like, reflective aluminum foil type of material. And in the center of the trough, you'll have oil and a pump that pumps it along, and all the sunlight bounces off the curved shape and into the middle of it. A solar power tower is, and they have these in Australia. I don't know about the US, but a water tower you may have seen, where you have a giant container of water. So what they have is, on the ground, there's a series of mirrors, and they all track the sun and angle the reflection of the light up at the tower to heat it up. Basically, the reverse of this is if you've ever taken a microscope or drawing a blank, what detectives look through, and you focus the light through, like Sherlock Holmes, and you focus the light through and you burn some ants, or you could start a fire that way. It's kind of the same concept, where you'll have this tower of water, and then all the mirrors track the sun and angle the reflected light up, then it heats the water. Then there's also this idea, and this is starting to happen with Tesla batteries and fuel cells at people's homes. So what you have is, you just have some water, and you use some solar energy, and it splits the water in half. So you pump electricity through it, and you will see this in Chem 162 when we talk about redox and electrochemistry. But if you run electricity through water, it splits apart into its separate elements. So it's the back reaction of this, right? You have liquid water, you run electricity through it via solar energy. You split it apart into hydrogen and oxygen. Now, the oxygen you don't really care about because it's in the air anyway. And then the fuel cell is basically a battery, an electronic version of combustion, where you combine hydrogen with oxygen and you get this energy back out. The problem with this is that hydrogen gas is flammable and very light. So you've been at a kid's birthday party, right? The helium balloon will fly away because the density is so low. Hydrogen's density is lower. So there's some logistic properties that make this difficult. This is one of the things when there's a difference between just seeing the energy here on the screen and then putting it into practice in the real world. Hydroelectric, right? This is, you're limited by the number of lakes and rivers and rainfall. And it has its own effects too, depending on what you care about. So, salmon can't swim upstream, they can't jump over dams, and silt and sand can't make it all the way down to the ocean. So it has its own effects. Everything has, a cause and effect. Then wind power works pretty good. So the Dutch have had windmills for thousands of years. The windmills that we have now here, at least in Hawaii, but that has its own problems other places, is salt. And so the materials are expensive. Fixing it is expensive. You got to stop it from rusting. And some of the other places they have these windmills, and it's usually in the desert. They're not the prettiest to look at, so people usually don't like them right next to their house, but they get a lot of dust in them, right? And there's moving parts and whatnot in there that need to be oiled. And again, things always sound easier and better on paper than they are in the real world. All right, here's our layers. This is the same slide from last chapter, but now we know a little bit more about the combustion and the heat and the things that have been going on, right? And so that ozone absorbing that energy, we'll talk about light coming up in the next chapters. That's what makes this temperature increase. And it's still, cold, what we think of as warm, right? There's room temperature ballpark. Then -50, and this doesn't get back up to a temperature that we call warm, but it certainly is much warmer than -60 or whatever. Okay, the same slides here. So air pollution added to the atmosphere. This is coming from all of us humans. But a lot of these same pollutants, they have natural sources. It's not like they didn't exist. So every time there's a lightning strike, and forest fires do happen naturally from lightning strikes and things like that, and volcanoes, as everybody on the Big Island knows. And we talked a little bit about the troposphere and these things that they interact, and you feel these with your mucous membrane, so your eyes, ears, nose, and throat. And we already talked about the ozone. SOx, again, we did this one, but it's just a good refresher here after we've covered these things. So coal has a lot of sulfur in it. And since you're burning it in a power plant, combusting it with oxygen, it's pretty easy for these type of reactions to happen. Then this is in the polyatomic ions we covered. It's not too tough to think that oxygen gas over time, and we'll get to some of this in Chem 162, but adding another oxygen to an element like this, they call these oxys. If they're acids, they're oxy acids. But it's not too hard for a central atom that already has oxygens on it to add another. So SO2 goes to SO3, right? Then here you're adding water, goes to SO4. So nitrogen, the same thing. And again, we saw these at the end of the last slide. So, and again, if you've flown into LA and the other city that's notorious for this, because sunlight helps, is Mexico City. And the reason it's those two cities in particular is geography. They have mountain ranges that trap in the weather, and the predominant wind flow direction doesn't usually blow the pollution out. So again, anything that has nitrogen in it when you burn it, so forest fires and lightning strikes, this is still, in volcanoes, this is still a natural thing because we have nitrogen and oxygen in the air we breathe, so any heat will create NO. And then combined with oxygen and water, you get uh, acid. Uh, and then it rains, and it's called acid rain. Okay, so now this combines a little bit more of our energy effects with the acid. So the prominent place that there's coal in the United States is where you see the highest acid rain, right? So I'm not a geography professor, but Florida is dead flat, right? It's basically the whole thing's a swamp. Swamp down here in Houston, it's pretty flat here. Then you get to right. If you've ever been before, it's basically Denver, right? Is this little blob, I think. It's really flat along here, right? They call it the Great Plains. And then Denver's like, it's a subtle uphill slope, but Denver is sort of the last place that isn't in the Rocky Mountains, right? If you've ever been to Denver, to the left of it is where the mountains shoot up and all the ski resorts are all to the left of it. So this is where hydroelectric is going to be, right? You got to have snow or lakes at higher elevation and flow down to the ocean. You're not going to have hydroelectric down here in Florida, right? It's at sea level. So the whole Gulf of Mexico relies on petroleum. Then the mountains in sort of the Virginias, North Kentucky, Tennessee, and up towards Ohio, uh, they're not that big, but there's a lot of coal here. So coal is hard to move, and you're definitely not going to move it up a mountain range when you have hydroelectric, or you could put oil on a ship and bring it to LA, San Francisco, Seattle, and refine it and ship it wherever, truck it or pipeline it somewhere else. And so we see this in the acid rain. Oh, this animation's funny where they zoom in as though we can't see it. And then you'll notice up here in Maine, you're getting further away. It's harder to reach it. It'd have to be, going by train, where it's easier now with petroleum to just take it on a boat and bring it somewhere closer than build a railway and go over mountains. And Vermont and New Hampshire and upstate New York, these aren't the biggest mountains in the world, but still. And then this is sort of the end of where the coal is. And so we see a pretty big increase in the pH number. So there's much less acid rain, right? And the predominant wind is from west to east, right? You don't, so again, LA is right here, this little dot, and the wind usually blows onshore. And so the smog gets kind of trapped in the LA, has sort of a hooking U-shaped mountain range. When the wind switch, the air gets really clear. So I don't know, next time you fly into LA, and it's more dramatic when there's more sunlight. So in the summertime, that's a bit more dramatic. And then here's the coal emissions, and not too shocking, are the SO2 emissions, which is basically coal. And again, it's going to be the states that are the closest to it. And then notice here all these little, like you're not well, Maine doesn't have a big population, but if you're directly along the coast, and I don't know if anybody is really dying to become a chemist and move into the petroleum industry, but petroleum in general, New Jersey has a huge petroleum industry. So when oil comes from wherever, the North Atlantic or the Middle East, even South America, the ships come up here and it gets offloaded, and then it's processed here to make gasolines and plastics and polymers and all kinds of things. So you're not going to take coal that's in these mountains and put it on a train over the mountains to get it to the coast when it's easier to just take the petroleum that's there. And then the wind isn't going to blow it the other direction, and you're not going to put it on a train and move it uphill. Now, a little bit of this has to do with also the population. So Florida is a highly populated state, and so is Texas, but Texas has its own oil, so it's not too surprising that Florida's is larger. But it's got to come. And then here, if you're in the mountains, it's downhill on a train down towards Florida. And I imagine most of this is the northern part of Florida. If you've ever been to Florida, I don't remember seeing a lot of trains taking coal all the way down to Miami's down here at the tip. Okay, so uh, a lot of freshman chem labs, you'll play around with a few different little metals that have been, and metals, if they're soft, are somewhat kind of like a block of cheese, where if you've ever made grated cheese yourself, and they don't, right, it's not as simple to do that, but you can make shavings and actually grind metal down to like dust, kind of like the way if you've ever grated cheese yourself. But they'll take that dust in these freshman chem labs, you react it with a little bit of acid, and you can see that it'll give off hydrogen gas. And so that basically tells you that metals that interact. Now, the acid rain that falls is less acidic than the acid you use in the lab. So it's a slower process, right? You use more reactive metals in the lab and use stronger acids, so you can see it happen on the time scale of the lab. But this does damage to the materials that we use, buildings and cars and bridges and all these things, and cement. And it can also change the pH or the acidity of levels of lakes. And so a lot of biochemical functions are pH, which is how you measure acid, are pH dependent. And so when the pH drops, biological functions, biochemical things, they don't work. And so a lot of times you'll see, not so much on the Big Island, but because the Big Island, the volcano erupting is pretty gentle and slow compared to some of the really more famous, nasty explosions of volcanoes on Earth. But every now and then, like you'll see this where they'll wear special suits, but if you see a lake that is perfectly clear at some volcano somewhere else on Earth, not Big Island, it's probably because it's incredibly acidic and everything in there is dead. Right? Think about a swimming pool. You don't see any moss really growing in it because there's a lot of chlorine killing what's in there. So sometimes really clear water, where if you don't see life in running water at all, it's probably hazardous. Dissolving, you should know that term, right? When you throw sugar in your coffee, it dissolves in and it takes on the appearance of the liquid. So sugar and salt are the most common cheap ones that we do in water. And then leaching means that there's something in the soil that the acidity changed the solubility of, and it makes its way out of the soil. It was encapsulated in the soil, in the dirt somehow, and changing the pH let that thing out, which is usually heavy metals, and then it goes into the drinking water and into the water table. It's not a law class or a history class, so but there was a Clean Air Act, and there's been a lot of push and move in pollution basically since the late 70s and 80s, when people started to realize these things and health effects and whatnot. So here's a picture after, I mean, with these things, like a haircut or something, you kind of need a before and after. But I'm assuming the original artist that sculpted this lion is what it looks like didn't do this bad of a job, right? I'm assuming this is, we need more info, but this has got to be like 500, 1,000 years ago, and it was probably impressive, and it's not so impressive anymore. It looks like it's melted. Then here you can see, this can't be from a forest fire, otherwise everything would be charred. This is the weaker leaves, etc. And again, a lot of biochemical and biological things don't function well at high pH, which is why the pH is high in our stomach, to help us dissolve food. CO gas, carbon monoxide, basically binds to your blood, and then when it's bonded to the blood, it doesn't come off as quickly, and so there's no way for your blood to grab O2 and deliver it. I actually have a friend in high school that his cousin passed away and died from CO poisoning, and he was near a boat that was idling, and they didn't turn it off, and there wasn't much wind, and apparently you just fall asleep, you lose consciousness, and you feel sort of drunk or something beforehand. So it can be a dangerous thing, and this is why one of the reasons we have catalytic converters on modern cars. But if you're around an old lawnmower, or a tractor or something on a farm, things that aren't don't have catalytic converters and haven't newly come off the assembly line or haven't been tuned up and taken good care of. But usually, right, gases expand in all directions. So if there's any breeze at all, it blows the gas away. Ozone, I think we talked about this, where there are some natural sources, and it's usually you need some really powerful thing like lightning, electricity, and then there's some chemical reactions in some really smoggy cities that generate it too. And it's similar to hydrogen peroxide. And in Chem 162, we'll look at the chemical shape and some of the electrochemical features that align ozone with hydrogen peroxide as well. And so I imagine everyone's put hydrogen peroxide on a cut or a scrape. It's pretty painful, right? So you wouldn't take a spray bottle of hydrogen peroxide and spray it in your eyes or your throat and your nose, right? And ozone is a very similar molecule chemically to hydrogen peroxide. All right, again, the book's a little dated. It was first printed in 2008, and there's been several editions, the newer editions, and this is one of the newer editions, but they don't fix some of the old data like this. They just fix typos and stuff. So anyway, there's around the 1980s, sort of on, late 70s is when people began to really become aware and make pushes to stop these type of pollutants. Right, and these are the same slides at the end of the last chapter, so we don't need to go through them in as great a detail. But ozone we do want up there in the stratosphere, but we don't want it down here where we're exposed to it. Again, it's like hydrogen peroxide. And here's the depletion, right? Again, we already talked about it. And those CFCs that are the bonds are really strong, so they're persistent and nothing washes them out or reacts with them down at sea level. And until they get up there near the ozone where that higher energy light is, that generates that chlorine atom, and then that's what does the destruction of the ozone. Those same pictures, but again, I'm not an atmospheric scientist or a geologist, etc. But anytime scientists want to study something that has to do with or without light, the poles are the place to do it, right? And Antarctica has land, so that's where they go and set up their instruments and whatnot. And so you're trying to predict the future, and so the way to do that is to look at a place that only has, now it has its own unique kind of weather and whatnot, but the extremes of light, where it's light 24 hours a day for a month and a half and then dark for a month and a half as well. Okay, 1:35. We do have some more time, but it's a little, I don't like starting a new chapter when there's only 5 or 10 minutes left to class. So this seems like a decent, a good place to stop, where we'll pick up next time. I don't even remember what the next chapter is, but there, I hit the unmute button. So kind of as usual, if you want to ask any questions, comments, thoughts, feelings, feel free to unmute, or even in the chat box if you don't want to talk. If not, we'll pick up on our next chapter, 7 of the PowerPoint, on Monday.
All right. See you Monday. Have a good one.
Sounds good, Ben.
Thank you, Professor. See you on Monday.
Cool. Bye. Have a good weekend. Feels weird to say that because I'm so used to Monday, Wednesday, Friday classes, but stop recording.